In this video, we will learn the final part, which is part 6 in chapter 3.1, and this is about semiconductors. By the end of this section, you should be able to explain conduction in semiconductors, explain electrical insulation. Previously also I told you something about semiconductors. The most common one we have is silicon. Germanium is also a semiconductor. You can see them in the periodic table. They are between the metals and the non-metals. By the end of this section, you should be able to explain conduction in semiconductors and explain electrical insulation. So we will learn conduction in semiconductors. We will see the valency band, the conduction band, and how this relates to conduction in metals, semiconductors, and why insulators are insulators in regard to this. Then we will see what conduction holes are, IV characteristic of a semiconductor diode. Remember, we saw the threshold voltage in the semiconductor diode, which was 0.6 volts. I will show you that again very quickly. Yeah, so now we are here in a different page, but we have seen this previously, the threshold voltage of 0.6 volts. This way the diode doesn't conduct. You can see the current is 0, but it has an almost 0 resistance after it passes the threshold voltage. That's why you have such a high current after this value is exceeded. And we learned about ohmic conductors, non-ohmic conductors. Now all of these are graphs of non-ohmic conductors. So if we quickly go through this, for the diode in figure D, we can see the basic idea that a diode only conducts in the forward direction, and so there is zero resistance for negative voltages. Zero current for negative voltages. It also requires a minimum driving voltage in the forwards direction. This threshold voltage is typically around 0.6 volts. The curve for a diode will be looked at in detail in section 3.1 part 6. So that's why I wanted to show you this. Now in the chapter part that we are going to discuss in this video, that is part 6 of chapter 3.1, we will see this in detail, which covers the ideas of electrical conduction in different materials. Okay, so we have seen all this. Now we are here. Then light dependent resistors are resistors whose resistance depends on the intensity of light falling on them. So I think we saw some pictures of light dependent resistors and also thermistors. Thermistors are resistors whose resistance depends on the temperature. In the case of LDR or light dependent resistors, when the amount of light falling on it increases, the resistance decreases. And similarly in thermistors, when the temperature increases, the resistance decreases. So you can see in both of them, when one quantity increases, the other quantity decreases. So here, when the amount of light falling increases, the resistance decreases. Here, when the temperature increases, the resistance decreases. Then insulators do not conduct or have a very high resistance, we can say. Superconductivity, I briefly explained in the very beginning all these things. So for metals, once you cool it below a certain temperature, it has an almost zero resistance, because the vibration of those you can say it, we will see the details. Okay. And finally you have the questions, and these definitions are very important. You can see here, critical temperature for a metal is that below which its resistivity instantly drops to 0. Remember, R equals rho L over A. We learned that equation for resistivity. So when resistivity is 0, the resistance is 0. Now this happens at the critical temperature. That is, when you cool a metal below its critical temperature, it becomes a superconductor because the resistivity drops to 0. We will see the details over here. So let's first start with what we have here in the beginning, conduction in semiconductors. Semiconductors are generally solid materials that only have small numbers of delocalized electrons. When we learned about metals, we learned about delocalized electrons, which are the conduction electrons, also called the free electrons. They are in the sea of electrons. So they can move around, and these are what make the metals good conductors. You have this delocalized or conduction of free electrons in semiconductors also, but when you heat a semiconductor, it releases more free or delocalized electrons, which make them even better conductors. Semiconductors are generally solid materials, for example silicon, germanium, that only have small numbers of delocalized electrons that are free to conduct. A typical example is silicon, one of the most abundant elements on Earth. Free atoms have a series of discrete energy levels in which we can find their electrons. So this is where we will see the valency band and the conduction band. So if electron receives enough energy, it will leave the atom altogether, leaving behind an ion. So you have learned that when an electron is added or removed from a neutral atom, it becomes an ion. For example, if an electron is removed from an atom, it becomes a positively charged ion, because in the beginning the number of protons and electrons in the atom, which makes it atom, is equal. So atom is electrically neutral, but when an electron is removed, you are removing a negative charge. So now it will have one more positive charge than the negative charges that are remaining. So okay, so here you can see silicon, one of the most abundant elements on Earth. Free atoms have a series of discrete energy levels in which we can find their electrons. Now you would have learnt about energy levels for chemistry, shells, energy levels, discrete energy levels in which we can find the electrons depending on the energy the electrons have received. See section 4.4.4. Now we are still in section 3. The next section we can see the details, but we can quickly have a look at what is here. Let's quickly go there now. Okay, we can try to see that later, but we'll first finish this. Depending on the energy of the electrons have received. If the electron receives enough energy, it will leave the atom altogether, leaving behind an ion. In solid materials, where there are many atoms close together, the allowed energy levels become much wider, forming energy bands. Okay, so here we have the energy band. So one is the conduction band and the other is the valency band. We will see those two here. So here remember these two bands. The electrons can have a large range of energies and still be within the same band. There are energy amounts which are forbidden for the electrons, but it is a very different situation from the highly limited energy levels of isolated atoms, electrons. As these energy bands are created by the collective grouping of solids atoms, the bands are attributed to the semiconductor as a whole rather than to individual atoms. There is an energy level called the valency band. Alright, so if you see this here you can see many atoms close together. The allowed energy levels become much wider, forming energy bands. Now compare that with this here. But it is very different situation from the highly limited energy levels of the isolated atoms electrons. Isolated atoms electrons, energy bands are created by the collective grouping of solids atoms. The bands are attributed to the semiconductor as a whole rather than to individual atoms. This is an energy. There is an energy level called the valency band. Electrons with this amount of energy remain tied to atoms and do not form part of any electrical current. So now you understand what the valency band is. So electrons within this amount of energy, that is the energy level for the valency band, amount of energy, remain tied to atoms and do not form part of any electric current. Now for them to conduct, they should be in the conduction band. So we will see that now. Those that gain energy to jump up to the conduction band become delocalized and can move through the semiconductor as part of a current. So now we are talking about semiconductors. So in the metals already electrons are in the conduction band. In insulators it is not. You can see here insulator has a full valency band. Semiconductor has an almost full valency band. But in the insulator the conduction band is empty. But in semiconductor almost empty conduction band. That means there are some electrons here. So it's not empty, but it's almost empty. This is not full, but it is almost full. whereas in the metal you have, see, almost full conduction band. Those that gain energy jump up to the conduction band become delocalized and can move through the semiconductor as part of a current. So for it to be conducting, for the material to be conducting, there should be electrons in the conduction band. Now this is an insulator because it doesn't have electrons in the conduction band. This is a semiconductor because it has some electrons in the conduction band. Metal already has almost full conduction band. That's why metals are good conductors. The gaps between energy bands within materials explain why they are conductors or insulators. If there is a large energy gap, electrons will need to gain a lot of energy to leave their atoms and conduct a current. So you can see that over here, see, there is a, look at the gap here, you can see from here to here. Here you can see it's very close, but here the gap is very large. So if there is a large energy gap, electrons will need to gain a lot of energy to leave their atoms and conduct a current. The gaps between energy bands within materials explain why they are conductors or insulators. Actually, there is a better diagram I will show you in the other book, or I'll show it right now. So here you can see how the energy bands are filled in a metal and in an insulator. Metal, you can see, see, conduction band has electrons. That's why it's in green. Insulator, it's not there, no electrons. But valency band in both, it's full. So for it to conduct, there should be electrons in the conduction band. You can see a valency band is shown, conduction band is also shown, and here is the forbidden gap. Now see, the electrons can be in these energy levels, but they can't be between the energy levels. So they have to be either in this energy level, or this one. They can't be in between. Those are the forbidden gaps, so they cannot exist there. It has to be in one of those bands. The electrons have to be in one of the bands. See, an electron can have an energy level at any level in one of the bands. See, electron energy levels. However, it cannot have an energy value which lies in the forbidden gap between bands, just as an electron in an isolated atom cannot have an energy which lies between two energy levels. And then, so here you can see in the semiconductor, now see, metal, insulator and semiconductor. See, conduction band. The electrons in the valency band can go there to the conduction band, and you can see that the gap between them, that is the forbidden gap, is very small. But here you can see it's quite large there. Narrow gap, valency band, electron energy bands in a semiconductor. Okay, all right, so let's go back to what we were doing. The number of delocalized electrons in a semiconductor is low compared with metals. The number of delocalized electrons in a semiconductor is low compared with metals, and so the current they will carry is therefore lower than metals for the same applied voltage. At higher temperatures, they have more conduction electrons. Now, I told you previously several times already that semiconductors become better conductors. They conduct better when they are heated because they release more free electrons or delocalized electrons. So more conduction electrons at higher temperatures. Why? As more electrons are elevated into the conduction band. So when you heat, more electrons go to the conduction band from here. I showed you that in the other book over here. So this is what happens. Now after that we will see conduction holes. So as a result you get these holes. Okay, so we will see what that is. There will be a temperature related reduction in current due to increased collisions with fixed atoms. Now in the case of metals you saw that this is significant. When you heat a metal, the resistance increases because the metal ions vibrate faster and also with a greater amplitude, which makes it difficult for the conduction electrons to pass through and conduct the current and carry the current, right? And here also it happens, but the increase in available conduction electrons far outweigh this. So compared to that vibration in semiconductors, it releases more free electrons. The overall effect is that a semiconductor will carry more current as the temperature goes up. Its resistivity effectively drops as the temperature rises. So this is for semiconductors, but not for metals. Now we will see about the conduction holes in semiconductors. When an electron enters the conduction band and moves away, this leaves the atom with an effective positive charge. The empty space the electron has left is referred to as a positive hole. If an electron from another atom moves to fill the hole, leaving its original atom with the hole has effectively moved, as the electrons will be attracted to jump in the positive direction of an applied voltage. So this happens when you apply a voltage, the electrons move towards the positive terminal of that power supply. The hole will slowly appear to move in the opposite direction. Because now if I draw a diagram also, I can show you. Now imagine, okay, let's go to this one. So imagine this electron is let's say going from this hole to this hole. So the electron is going from left to right, let's say. Then the hole is going from right to left, because the one electron comes here, so the hole goes the other way. That is what is meant by this. As the electrons will be attracted to jump in the positive direction of an applied voltage, the hole will slowly appear to move in the opposite direction. A positive hole moving towards the negative cathode is effectively another charge carrier. So the positive hole is going from right to left. In other words, you can think of it as a positive charge moving to the left. Cathode is effectively another charge carrier, contributing to the current flow in a semiconductor. It is analogous to the current flow in electrolysis, where positively and negatively charged particles are moving in opposite directions at the same time. So very simple. So here now you understand conduction holes, and you can see this is what happens in semiconductors. So this is contributing to the current flow in a semiconductor. Then we learnt about the valency band, the conduction band, and we learnt about insulators, semiconductors, and metals. Now see, in insulators the conduction band is empty. Semiconductors, it is almost empty, but once you heat, what happens? The electrons can go there. Then valence, now in the metal, almost full conduction band. So the conducting electrons are in the conduction band. So if you have more electrons there, it will be a better conductor. Note that conduction by holes does not mean there is overall movement of the positive lattice ions. So positive charges don't move. But what happens is the electron is going from right to left, from one place to the next place. So that's why there is a positive created from right to left. It's not the positive charge moving, but it is the electron that are moving from left to right. We saw it here. So remember, the protons can't move. The positive ions can't move in a solid because they are fixed. But the electrons can move. So electrons, when they go from left to right, it's like a current flowing from right to left. Does not mean there is overall movement of the positive lattice ions. The holes are an absence of an electron, and it is this space that seemingly moves as electrons actually jump in the opposite direction. Then previously I told you we saw this IV characteristic for a semiconductor diode. A diode is made by joining together different types of semiconductors. So diode is made up of semiconductors, which normally create an energy barrier at the junction between them, blocking the movement of charge carriers, holes, and electrons across the barrier. So this barrier can overcome in the forward direction if a small forward voltage is applied. In the reverse direction, only very few charge carriers can pass through at low voltages. They account for a tiny leakage current. Now you can see once the reverse voltage becomes large enough, it can overcome the large reverse energy barrier and force the conduction process in the opposite direction. So far we didn't learn about this, but we learned this in the previous section or previous part of this chapter 3.1. we saw this, but we didn't see this part. But you can see this can happen once the reverse voltage becomes large enough. It can overcome the large reverse energy barrier and force the conduction process in the opposite direction. Forward junction potential, forward conduction, reverse breakdown voltage. So after this it starts conducting. So leakage current, see here, reverse breakdown voltage, that is this, and after that it starts conducting. Now here this is the leakage current. So after that the current starts flowing, and then after this value, the reverse breakdown voltage, it starts conducting. The IV characteristic, or in other words the IV graph, is what we call IV characteristic for a semiconductor diode in detail. And then light dependent resistors have the property that their resistance depends on the light level around them. In brighter conditions, the LDR will have a lower resistance. LDRs are made from semiconductor material, and light landing on the material can boost electrons from the valency energy band up to the conduction band, increasing the number of conduction electrons. The effect of this is to make the LDR conduct better. It has a lower resistance. Thermistors work in exactly the same way, except that their resistance depends on thermal energy from the surroundings. The most common type of thermistor are referred to as negative temperature coefficient thermistor. So that's what I told you previously in the previous video, NTC thermistor, negative temperature coefficient thermistor. So if they don't tell you what type of thermistor it is, by standard it is an NTC or negative temperature coefficient thermistor. These use thermal energy to boost their electrons into the conduction energy band, meaning their resistance falls as the temperature rises. But in the PTC thermistors, positive temperature coefficient thermistors, it's different. When the temperature increases, the resistance also increases. So then insulators, obvious. Let's see anyway, we'll go through this. Electrical insulators can be thought of as materials in which the energy gap between the valency band and the conduction band is so large that there are virtually zero electrons available for conduction. So you see, I mentioned about the gap previously, the energy gap between the valency band and the conduction band, that was called the forbidden gap. So over here you can see this forbidden gap, that is what is between the conduction band and the valency band. Can be thought of as materials in which the energy gap between the valency band and the conduction band is so large that there are virtually zero electrons available for conduction. There will therefore be no conduction holes either. A very large input of energy is required in order to make the material conduct, that is insulators. So for example, even an insulator can conduct if the voltage across its ends is so high. Now in the case of lightning, even if a person wears rubber slippers, if there was a lightning strike, then the current passes even through the rubber slippers. Rubber is an insulator. There will therefore be no conduction holes. A very large input of energy is required in order to make the material conduct. Often this results in melting or other damage before the material becomes electrically conducting. For example, glass is normally an excellent electrical insulator, but at a very high electric field, more than 10 million volts per meter created across glass can cause it to become conducting. Then superconductivity. So this is where we saw critical temperature. Now you can see this is an ammeter, high energy plus battery, and here is the metal that we are testing, and the wires are here. So you can see like that. So the metal is here. Now this is where we reduce the temperature of the metal here and see what happens to the reading here. Resistance increases with higher temperatures. because the energy levels of higher level of internal energy in the material causes more vibration of fixed ions, so the metal ions, and they collide more often with the charge carriers to reduce their speed of movement through the material. Reducing the temperature therefore reduces resistance, allowing greater current flow. If we cool a conductor, the current through it is seen to increase because its resistance drops. So I told you the reasons why it increases and why it decreases, because the vibration of the metal ions decreases with decreasing temperature and increases increasing temperature. Cooling to even lower temperatures continues this trend until something quite unexpected happens. Below a certain critical temperature, the resistance suddenly drops to zero. This is called superconductivity. So you see, that is superconductivity. The critical temperature varies with material, but for most metals it will be below minus 243 degrees Celsius. Complex ceramic superconductors have been created that have temperatures at which they conduct without any resistance as high as minus 135 degrees Celsius. Now if you look at the number line, this number is more to the left, which means it's much lesser than this number. Superconductors are especially useful in applications where a large current is needed, as a large current would normally waste too much energy or damage the surroundings with the heat dissipated. So we can get a large current without causing it to heat if we reduce the temperature and stop the vibration of those metal ions, let the electrons pass through. So we rather than saying stop, it is so less, we can say that the electron can pass through easily, which reduces the resistance to zero. As a large current would normally waste too much energy or damage the surroundings with the heat dissipated. For example, the strong magnets needed in a particular accelerator will often be superconducting electromagnets. So, cool to very low temperatures to maintain their superconductivity. The electromagnets in the LHC, also called Large Hadron Collider, operate at about 1.9 kelvins. Okay, so here you can see strong magnets, then the critical temperature, you learned what that is, then you learned what superconductivity is. So this is called superconductivity. Then applications are useful in applications where a large current is needed. So we saw that. For example, the strong magnets needed in a particular accelerator will often be superconducting electromagnets, cooled to very low temperatures to maintain their superconductivity. Let's see this. Low temperatures are often expressed on the Kelvin scale, where 0 kelvins is referred to as absolute zero. 0 kelvins is minus 273.15 degrees Celsius. You should know this unit conversion. So always the Kelvin value is higher than the degrees Celsius value. Okay, so 0 Kelvin is minus 273.15. Now if you want to convert from Celsius to Kelvin, you add 273. So 0 degrees Celsius in kelvins, you add 273 to this number, it will give you 273 kelvins, 273.15 to be more accurate, to 2 decimal places. See, we usually ignore the 0.15 degrees. This we usually don't write, okay? But when we say Kelvin, we don't say degrees Kelvin. When we say Celsius, we say degrees Celsius or degrees centigrade. And convert from Celsius to Kelvin by adding 273 degrees, okay? Celsius, from Celsius to Kelvin by adding, yeah. Actually, I think I have created a video about this unit conversion. It's in the O-level physics playlist. You can have a look. There's a way to write the equation so that these units cancel out properly. Absolute zero is the lowest temperature possible, as this represents a temperature where the particles have zero internal resistance. Then here you can see superconductors can levitate magnets, as they do not accept penetration by magnetic fields. This is the Meissner effect. So what is the Meissner effect? Superconductors can levitate magnets. Why? Because they do not accept penetration by magnetic fields. Superconductors, we can say, do not accept penetration by magnetic fields. As a result, they levitate magnets near them. This effect is called the Meissner effect. Okay, we have come to the end of the chapter. Make sure you answer all these questions. Then key definitions: semiconductors have a lower resistivity than insulators. The lower the resistivity, the lesser the resistance, because from the equation you can figure it out. R resistance equals rho L over A. So when rho decreases, the resistance decreases. So lower the resistivity, remember that equation. If you can't see it, you can write it down. R equals rho L over A. R is the resistance, rho is the resistivity. So when rho decreases, you can say from that equation R, the resistance decreases. Semiconductors have a lower resistivity than insulators but higher than conductors. So so like I said, when the resistivity increases, the resistance increases. So semiconductors have a lower resistivity than insulators. Then conductors or metals have a lower resistivity, we can say, than semiconductors. They usually have only small numbers of delocalized electrons that are free to conduct, that is semiconductors. The valency band is a range of energy amount. So you can see the definitions are given here in the exam. If they ask you what is the valency band, what is conduction band, what is critical temperature or defined critical temperature, you can write this. What is a semiconductor, you can write this. The valency band is a range of energy amounts that the electrons in a solid material can have, which keeps them close to one particular atom. And you could see it somewhat in detail here. See, these are the energy bands. See, it has several energy levels. So now we'll have a look. Is a range of energy amounts that electrons in a solid material can have, which keeps them close to one particular atom. Conduction band is a range of energy amounts that electrons in a solid material can have, which delocalizes them to move freely through the solid. The critical temperature for a material is that below which its resistivity instantly drops to 0. So now you know the meanings of all these words. Make sure you memorize them with understanding, because in the exam paper they can ask you what is critical temperature. If you try to write it in your own words, you might miss certain keywords. For example, resistivity. So if you miss those keywords in a definition, you may not get the full marks for that definition. That's why I tell you all to memorize it with understanding. Okay, so that's the end of chapter 3.1. Make sure you answer all these questions over here, as well as the questions which are spread out through the chapter, and answer these exam style questions or end of chapter questions. Check all the solutions to your answers in the answer script. And next we will see chapter 3.2.